Let's do our first example over entropy right now. And in this problem, we're going to have 1 kilogram of water. It's contained in a piston cylinder assembly. Temperature is initially 160 degrees Celsius. Pressure is initially 150 kilopascals. This is going to undergo an isothermal compression process to saturated liquid. For this process, work is going to be negative 471.5 kilojoules. We need to find our heat transfer and the change in entropy. And the change in entropy, the units need to be kilojoules per Kelvin. So let's get started on this one. First, let's draw a simple picture. We got a piston cylinder assembly, looks like this. Got 1 kilogram of water. Notice work is negative, so that means there's some external energy that's causing this piston to move. All right, so let's write that. So that's a picture of the problem we have, and let's write out our values for the states. And before we do that, let's also look for our keywords. So this tells us we're undergoing an isothermal compression. Remember what that means, no change in temperature. So that's going to be important to see that, and we're going to saturated liquid. We're starting out at a temperature of 160 degrees Celsius. Pressure is going to be 150 kilopascal. Now I want to convert that over to bar because that'll be easier in just a second. So let's go ahead and do that now. Remember, the conversion is just 1 bar per 10 to the second kilopascal. So that gives us 1.5 bar because those go away. All right, so that's our pressure at the start. So this is T1, P1. And then at state 2, we've got our temperature. What's the temperature going to be? 160, that's right. And we also know we have saturated liquid. That's what we know for state 2. Now we need to find heat transfer, so we need to find Q. That's what we're looking for. Now remember, we need energy balance when we're finding Q. Which energy balance equation do we want? Do we want the simple one, or do we want that lengthy one with mass flow rates? We want the simple one because this is a closed system. So we don't care about any mass flow rates because we don't have any mass that's flowing. That's going to lead us to delta U plus delta KE plus delta PE equals Q minus W. With this piston cylinder assembly, are we going to have kinetic energy and potential energy? That's really going to change anything? Nope, those go away. So we are simplifying everything, which is good. Now Q, if we solve for Q, is going to be delta U plus work. Now remember, this is regular internal energy. All right, this is not specific internal energy. Our tables give us specific internal energy, so we need to rewrite this in terms of specific internal energy. And if we do that, we're going to have Q equals the mass times specific internal energy at state 2 minus that at state 1 plus work. Okay, so now we're here. Now you got to find these values in the table. So that'll be our next thing we need to do. We need to find U2. That one we have saturated liquid. If we have saturated liquid, that one is easy to find in the table. What we're going to do, we get saturated liquid, we go to our saturated water table, we look up temperature is 160, and then we just look over here and we get saturated water. So we got 674.86. So that's our value we need for U2. And that's kilojoules per kilogram. And that was from table A2. Now A1, not A1, U1, we are at the same temperature, but now we have this pressure. And we don't know what we've got. So we've got this pressure of 150 kilopascal. So if you look again at this table, find your saturation pressure. Our pressure is a lot higher than that. So that means we're going to have superheated vapor. So we're going to have 2590, whoa, that's the wrong number, 2595.2 kilojoules per kilogram. All right. Actually, guys, I said that wrong. I was looking at 150 kilopascals. We're actually at 1.5 bar. This pressure here is in bar. So our pressure is, the saturation pressure is 6.178. Ours is at 1.5. Okay, so we're less than that. So that would give us superheated vapor. That makes more sense. Okay, so this one is going to come from table A4. That's the superheated vapor table. Now that we have all that, we can plug everything into this equation for Q. So Q is going to be the mass, which is 1 kilogram, times 674.86 minus 2595.2 kilojoules per kilogram. And then we've got our work. We were given that. It was negative 471.5. That was kilojoules. Notice kilograms cancels with that, so everything is in kilojoules. And you get a Q of negative 2391.84 kilojoules. So that is our heat transfer in kilojoules. Now we're at part B. So this one we want to find the change in entropy. In order to find that, we have to find the entropy at state 2 and then entropy at state 1. Now we already know at state 2 that we have saturated liquid. So for this one, you just look in the saturated water table at a temperature of 160 and pull out the entropy value for saturated water. So at 160, you're going to go all the way over here, get to saturated liquid, so you get 1.9427. Notice your units, kilojoule per kilogram Kelvin. So let's write that value down. All right, and remember this is specific entropy. So this was from table A2. And then we're going to do the same thing at S1. We're going to go back to the table that we used to find this. That's the superheated vapor table. So if we use that, we're at a pressure of 1.5 bar and a temperature of 160. So here's the pressure, here's our temperature. S is over here. So 7.4665. All right, and units are the same, obviously. So now we've got that. This is specific entropy, whoops, also, and this value is from table A4. Now, it didn't ask for change in specific entropy, it wanted regular entropy. So let's set that up so that we get entropy. All we need to do then is get rid of the kilograms in the denominator. And how should we do that? That's right, we're going to multiply by mass. So we're going to have mass times S2 minus S1. Our mass was 1 kilogram. So essentially you just have 1 times the difference of these two. Alright, so subtract those two numbers. Make sure you include your units. Notice the kilograms goes away. That's going to leave us with a change in entropy of negative 5.5238 kilojoules per kilogram. Now if we look at this value right here, notice we have a negative. So if you look back here at this equation, that means S1 is higher than S2. So our entropy at state 1 was higher. Remember we said entropy, you can think of it as disorder. Now if you look at what we had, state 1 we had superheated vapor. All right, so we had vapor, we got lots of particles moving around, and then state 2 we have saturated liquid. So it makes sense that the entropy at state 1 is higher than at state 2, and that gives you that negative sign. All right guys, that's the end of that one. I will see y'all in the next video. Y'all have a great afternoon.